We discussed web, email, and DNS applications by far. These applications have a client-server architecture. We are now going to discuss another class of applications, which are peer-to-peer applications. Remember that in client-server architecture, we had an always-on server with known IP address. The known IP address was used by clients to contact the server. In peer-to-peer architecture, there are no always-on servers, and two end systems can communicate with each other directly. The end systems, called peers, are intermittently connected and change IP addresses. Skype, which is a famous video conference tool, BitTorrent for file distribution, and ConCon for streaming are examples of peer-to-peer network applications. To start our discussions, let's do a comparison analysis on file distribution in client-server and peer-to-peer architectures. Assume our file size is F and it is on a server. To distribute the file needs to be sent or uploaded from the server and received or downloaded by the receivers. We want to find out how much time it takes to distribute file of size F from one server to n receivers in each of the architectures. Let's discuss what happens. In client-server architecture, for each client that requests the file, the server needs to upload the file for the client to download it. Therefore, for end users, server uploads the file n times and each of the end clients downloads it. So, if US is the server upload capacity and UI and DI are each client's upload and download capacity, with file size F, time to send one copy from the server will be F divided by US. With n clients, the server has to send the file n times in response to each client request, and the time to send n copies will be n times F divided by US. This increase will be linear in n. Each of the end clients must download the copy sent by the server. The time it will take for client I's download is F divided by DI. Among all clients, the slowest client will take the longest time. So the longest time will be for the client with minimum download capacity, which is dmin. Therefore, the longest time will be F divided by dmin. So, the total time to distribute the file with size F to n clients using client-server approach will be lower bounded with the maximum of n server uploads and the longest client download, which is maximum of n times F divided by US, which increases linearly in n, and F divided by dmin. Now, the peer-to-peer architecture. At the beginning, only the server has the file. The server needs to upload at least one copy of the file. Each client must download the file. Remember, the longest download belongs to the client with the minimum download capacity. But each client, after their download, can contribute to the next uploads. And therefore, some of their contributing upload capacities could help reduce the upload time. The lower bound could be met when each peer starts distributing a bit as soon as it receives a bit. In reality, chunk-level contribution is made, therefore we are aiming at an approximation here. So, uploading one copy from the server will still be F divided by US. Each client I downloading a copy will still take F divided by DI. N clients will download n copies, so the download size is still n times F. But they will also upload using their UI capacity. So the lower bound for the delay will be maximum of F divided by US, which is server upload time of one copy, F divided by dmin, which is the download time of the client with the minimum download capacity, and NF divided by US plus sum of UIs, which is the upload time of N files using aggregate client and server capacities. NF increases linearly in N, but so does the denominator as the clients receive a copy and start uploading. Therefore, as you can see in this figure, the peer-to-peer architecture will show lower distribution time when distribution over higher number of peers is required. This is the direct result of redistribution by peers, which is the auto-scalability characteristic offered by the peers to the peer-to-peer architecture.